So I am Steve Miller. I'm a math professor at Williams College. I also serve on the Mount Greylock Regional School Committee. So I have various experiences along those lines that I can talk about when there's equipment malfunction and it's not recording. I also just recently received a grant to do math outreach using Legos and Rubik's Cubes, which I'm happy to talk to people about. I don't know if I have to do all that in the Berkshires. I'm always up for visiting people at their schools. If you're able to pay transportation expenses, that's great, but it's not necessary. Other things, I want to thank the Journal of Number Theory and our publisher Elsevier, which has provided a lot of money for a lot of these outreach activities. Before we get into cryptography, I just want to follow up on a remark of Henry, who basically pigeonholed when I began this program by the Boston Red Sox, in their championship seasons. I will always take an opportunity to talk about the Red Sox. So when I was young, my great-uncle Newt swore to me that I would live long enough to see the Red Sox win. And in 2013, I woke up my son, who would have been, let's see, he was born in 2007, so I will let you do the arithmetic, and I brought him downstairs in like the 8th inning when it looked like the Sox were about to do it. And he's half asleep, but he's slowly waking up, and he kind of watches it, and he's kind of like falling in my arms as I bring him back to bed. I said, Cam, Uncle Newt promised I would live long enough to see it. I have, and now you have. And in a half asleep voice, he goes, I did it earlier than you did, Daddy. But the reason I'm bringing this up, not just for talking about the Red Sox, is there's a lot of different ways we can take the 2 days we have. I do not have a set curriculum that I want to do. I want to do whatever's going to be most useful, most entertaining, most exciting for you. One of the many ways you can go with cryptography is it's not just about transmitting information. A lot of it is misdirection. What information do you want the other side to have? So who here is a huge Red Sox fan? Okay, let's talk really bad signings from the Red Sox. Pablo Sandoval, I'm sure, is going to be at top of the list in recent history. Anybody know another really bad recent history signing? Signing for the Red Sox. He then went to the Dodgers as part of a monster trade. Outfielder originally from Tampa, Carl Crawford. Oh, Carl Crawford. So you can look up how much the Sox paid for Carl Crawford. Oh yes, yes. One of the many disasters. The New York Yankees.
It's important as a Red Sox fan to be able to forget.
Well, with enough rings, you can forget.
You can't make it then.
No. But the Yankees feigned interest in Carl Crawford to drive up his price, and the Red Sox paid more for him. So one of the really important things when you're doing cryptography is what information do you want the other side to have. So if you want, I'm actually able to give lectures on mathematics and baseball. And so these are tangentially related to cryptography, but if you want to see applications of basic probability and calculus to baseball, that's something we can definitely do the next time.
Oh, I should mention if it can work with Steve's schedule and it works for you, is I can sponsor his coming to your school, working with a group of teachers, colleagues, whatever, and I pick up half his stipend costs, but I ask the school to put a little bit of money for it also. But he's done these in the past, and I think they've been a lot of fun. Something to keep in mind.
Okay, so anybody want to tell me roughly what cryptography is?
Sorry, what was the question?
Roughly, what is cryptography? Well, what do you think of when you hear the word cryptography?
Putting things in code.
Putting things in code.
And decoding.
And decoding. So this is encryption and decryption. So you want to encrypt, and you want to be able to decrypt. And there's a word that's often not put in, but should be. You want to do it efficiently. So there are some things that can be done, but the universe would die a heat death billions of times over before we can finish running it, and so it's not really useful. In World War II, they had different levels of encryption. Let's say you're in a battlefield situation, and you want to give orders to some troops near you as to what to do. You adjust your shelling by this much, enemy coming from here. This is information that only needs to be secure for on the order of a few minutes. If it takes the other side 2 hours to decrypt it, that's fine. There are other things such as planning for the D-Day invasion, where that's information that must stay encrypted for several months. And so you would want a different level of security. So if you've watched movies like Code Talkers about the Native Americans being used, you want to be able to have conversations in real time and not have to spend a lot of time encrypting and decrypting. So a lot of it is about hiding things. And so we'll start with some classical ciphers that were used to encrypt and decrypt information, and then we'll try to go into some of the modern stuff. And I want to try to emphasize the good math that comes in. And so frequently you don't have to use the most advanced mathematics to do something valuable. And one of the things we will do today, this is the first time I'm ever giving this talk, I'm very excited about it, is the German tank problem. And so I'll talk about that a little more. How many people have done Rubik's Cubes? Or at least seen a Rubik's Cube? They made a nice appearance in one of the Despicable Me movies, I think the third one. So I'm not even going to bother bringing a standard Rubik's Cube. Everybody knows what they look like. I'm bringing in some non-standard ones, and I'll pass them around. They look at least the right shape, but this one is, 2 by 3, and it's got like a strange kind of, this one is at least 3 by 3, but it can't turn the same way. So the question is, how do you solve these cubes? And they look a lot worse than the standard cube. So the first one I saw like this was, I was visiting my daughter's class in, it would have been 3rd grade. And they had a version of this, except it was all one color, and they were different sizes. So they were using size rather than color to indicate where things were. And I just couldn't figure out what it was. And then, well, my daughter had a baseball game there, that I've been playing with it during the baseball game, no luck. And the next day in the morning, in 1 second I figured out how to do it. It's almost the same as a regular 3 by 3. It's the same as a 3 by 3 if you have pictures on the sides. So for instance, if you have a cube where the sides are all one color, and there's no picture, you can't tell if the center square is rotated. So if you know how to solve a cube where the centers have pictures, and you know how to deal with that, this is the same as one of those. You have to know how to hold it. And the reason I'm starting off the cryptography lecture with this is, in some sense, this is an encrypted 3 by 3 cube. Which do you think is the front side of this cube? Is this a legitimate candidate, the red as one of the sides?
Wouldn't they all be a candidate?
Say they should all be a candidate. This red is not a side of the cube.
Why not?
You have to hold it at a 45-degree angle right at you. This is the front face. And then this is going forward and back, forward and back. So really, this whole thing, half green, half red, is really one of the faces. The yellow and the white are the more standard ones like that, because they don't twist differently. But if you hold it at a 45-degree angle, it's essentially the same as a regular cube.
So in other words, if you know how to do the regular cube.
If you know how to do a regular cube, you know how to do
it,
this.
you're still up.
You're still out of luck. But you can at least say, oh, it's the same as a 3 by 3 when you just put it down.
Yes!
And the hand has to move up like this. But it's a great example of how things all around you can look much harder than they actually are if you just find the right perspective to look at them. So I start all of my math classes with stuff like this. This cube is really the same as that one, except it's 30 degrees or 60 degrees, depending on how you like to hold things. This is probably my favorite cube. Anybody know how many sides? 12. So I said, oh, you do 6-sided cubes? But if you think about how many pieces this has, the number of pieces of this is more than a 2 by 2 by 2 cube, less than a 3 by 3 by 3 cube. This cube is really only slightly harder than a 2 by 2 cube. But it looks much worse. And just for the reason I like this is, if you can solve one of these cubes, how do you pass that knowledge on to something else? And so when you're learning how to solve cubes, a lot of people teach you fast ways to solve cubes, which I don't like. I prefer the slow way that teaches you, here are moves that will probably generalize.
Like an algorithm.
Like an algorithm. And this algorithm will look slightly different depending on which cube you look at. So I can apply a very similar algorithm for the 2 by 2 and the 3 by 3 on this. And I just have to figure out how to adjust it for the fact that this is not a cube anymore. But a generalization of that algorithm works. Those sequences of steps work. We're going to want the same thing when we start doing codes. I want to do something simple, and then I want to generalize it and make it a little bit more complicated, but really have the same essential ideas. So there's a lot of great stories on historical codes. One of my favorites was, if you have slaves, you can do lots of things to them, such as shave their heads, write a message on it, wait for the hair to grow back. Now, there's a lot of issues with this. One, of course, is if the slave is captured and they think to shave the head, your message is displayed. The other thing is you really can't accelerate hair growth that quickly. Okay. I was just seeing if there's anybody who knew. I mean, I'm actually pretty good for hair. My Uncle Bob still has this full head of hair, so I'm not that worried, but I was just wondering if anybody's, oh, no, there's this really great method. Okay. So the first, really good encryption that I want to talk about is the Caesar Cipher. There were others, wrapping things around rods at fixed lengths, and then having things line up perfectly. There's, a whole slew of stuff you can do. Wikipedia is wonderful for stuff like this. As a mathematician, I love to work with numbers and not letters. How many of you have ever done any probability? Okay, good. So in probability, we love to work with numbers. And the reason is, what's 3 heads and a tail? 3 heads and a tail. We really can't do anything with it. But if we say a head is +1 and a tail is -1, or a tail is 0, we can then start to add the heads and the tails. We can have ways to combine them. So rather than working with letters, we like to work with numbers. So work with numbers. And there are 2 ways we can do this, really. We can work base 2, or binary, or we can work base 10, which is the standard decimal system. For computers love base 2. On, off, yes, no, true, false, Red Sox.
The evil empire.
The evil empire, absolutely. So for computers love 0, 1. And it's not that hard to go from 0, 1 to base 10. So if I do binary, so 0 would be 0, 1 would be 1, and then 10 would be 2. Because this would mean 1, 2, and 0 ones. 11 would be 3. And if you're counting on your fingers, you've got to be very careful at this point. That would be 4. And so on and so on. So what we could do is, if we wanted to write letters, well, we've got 26 letters in the alphabet. Then we've got probably the numbers, the digits 0 through 9. Then we've got some punctuation marks and whatnot. 64 characters should probably be enough to convey all the standard letters, punctuation marks, and whatnot.
7 digits.
So that would be about 7 digits. So over here, if we go all the way up to 1, 1, 1, that would be the number 7, and that would give us 8 things to encode. We start counting at 0. My son learned at an early age that as a mathematician, if I said you can do it 3 more times, he would start counting with 0. And he knew I would be so happy that he could get away and do it 4 times. So with 3 digits, we can get up to 8, 4 digits, 16, 5 digits, 32. Am I doing it right?
Yeah.
So 6 digits would be 60.
Usually,
You count the character 0.
yeah, usually don't
So
have
that's
0.
there's your 64.
You need the 7th digit for your 64.
Well,
And the
you
number
want to
64,
transmit
number
60.
side, you still have
Right. So if I wanted to transmit the number 64, yes.
Yeah, so 64 digits
Was-
or 64 characters
Would be
6 digits.
right. So we could have strings, 0, 1, 1, 0, 1, 1, 2, 3, 4, 5, and that would represent one of my 64 choices. Okay, so it's enough to transmit zeros and ones, and if we can do that, we can always have a lookup table to convert from strings of zeros and ones to letters and back and forth. Okay, so not surprisingly, when this stuff began, they didn't start off with numbers, they started off with letters. And when Caesar was having his armies advance, so many people were illiterate, you almost didn't need to encrypt anything. Just writing it down was essentially enough. And I think he wrote things down in Greek to make it even harder for some people. But so the first, my spelling is terrible, is it A-E?
A.
The Caesar Cipher. And I believe I encrypted the title of this class with the Caesar Cipher. I got some raised eyebrows from the registrar at Williams when I first taught this class as I went to study with that as the title. And are you sure you want to? And I said, absolutely. And several of my students told me that it worked when they were being interviewed by companies. They said, yeah, we gotta ask, what was this on your transcript? And it shifted the conversation to something that they would have fun talking about. So the idea is you just add 3. You can do, of course, other shifts. So the letter A, if you add 3, goes to D. B goes to E. W goes to Z. And now the only slightly interesting part, X goes to A. So we just wrap around. So this should remind you of a clock. Unfortunately, we have an old clock on the wall. You know, everything else in the building is nice and new, but we have this old-fashioned clock with the numbers, 12, 1, 2, 3, all the way up to 11. And you just wrap around. So it's basically, we'll call it 10 o'clock now. In 5 hours, it would be 3. So we know how to add numbers on a clock. We just wrap around. It's the same thing here. So this is called clock arithmetic or modular arithmetic. So this is a really nice, simple system. It's very easy to encrypt. It's very easy to decrypt.
This is why they would have decoder rings when you were a kid.
Yeah.
Decoder rings.
Now, what is the problem, though, with this system?
It's very easy.
It is very easy to decrypt. So imagine I give you a message encrypted using the Caesar Cipher. How many tries, worst case scenario, would it take you to crack?
What constitutes a try?
Is it always add 3 or could be add
It could be add anything. So this is add 3. Let's say we don't know. Now it's add some unknown number. We don't know what the shift is.
Okay, so we have to figure out that.
Right, so how many shifts could there be?
26. Yeah, but it wouldn't be 26 tries.
Okay, why 25 and not 26?
One week.
Yes, yes. Hopefully, if you are going to encrypt, you are not going to encrypt with a shift of 26. But you have to be careful. So this introduces a really nice point in mathematics. Sometimes it's easier when you do the counting to include the trivial thing like that. Otherwise, you sometimes have to worry about as things get more advanced. If I'm eliminating those trivial cases, the counting formulas may become harder. In practice, I probably will not choose the shift by 26. Now, if you happen to know that somebody's going to try to decrypt it by shifting, and they'll try all the shifts from 1 to 25, then actually the best way to encrypt it would be to shift to 0. But it's unlikely that somebody would miss something like this. Okay, so there are only 25, there are 25 Caesar codes. This is not great, right? It's not going to take you that long to figure it out. And you probably don't have to decrypt the whole message. And what's nice is if you're trying to shift, well, you know what the next letter is. So if you shifted it by 1, just keep incrementing by 1, it's not that hard. So we want to have something that's a little bit more involved. So let's try to look at mathematically what we're doing. And if I'm ever using notation that is not familiar or it's been a while, if you speak up, almost surely someone else in the room will be grateful. They probably won't show their gratitude, but they will be grateful. So here is the Caesar code. I take X as an input, and I add 3. I've got to be a little bit careful, because we have to do wraparound. So what we do here is mathematically we will write mod 26. So how many people have not seen mod symbols before? Okay. So we say X equals Y mod 26 if 26 divides X minus Y. So you've seen this on a clock. You've seen things mod 12. So clock, 10 equals 3. 10 equals. 15 equals 3 mod 12. I was doing, it's 10 o'clock now. In 5 hours, it will be 3 o'clock. So 10 plus 5 is 15. But on a clock, 10 plus 5 would be displayed as 3. Because we don't have those expensive 24-hour clocks. But if we did, we could do everything, but we just do it mod 24 rather than mod 12. So two numbers are equivalent if they differ by a multiple of 12 here, or if they differ by a multiple of 26 here. Sometimes mathematicians like to put 3 symbols to just emphasize that we're not saying that they're equal, we're saying they're equivalent. Notation is very valuable. You want to be able to quickly glance down and see what's happening. Okay, so this is the Caesar cipher. This encrypts. It's a very easy function to write down. We want a decryption function. So we now take some output of this, let's call that y, and we want to get back the original message. What do you think the decryption is? Yeah, y minus 3. So the C is to just remind myself that this is the Caesar cipher. And so we're going to have lots of different choices. I want to be able to quickly glance on and say, these are the codes for Caesar. What's nice is essentially it's the same encrypt and decrypt. So you could actually even change the code a little bit. Maybe Fn of x is x plus n mod 26. And so maybe I'll use my subscript to just note what is the shift. And then the decrypt would be f of 26 minus n. And so I would know exactly what to pair it with. Okay, so the Caesar cipher, if people don't know how to read, it's essentially enough. If you know that somebody has encrypted by just shifting all the letters, then the Caesar cipher is terrible. So we want to do something a little bit more secure. So you've almost surely seen where we're going to end up, but I want to get there in stages. I want to look at what's the next most complicated thing we could do. Well, this looks like a linear function. Is this the most general form of a linear function? So what would be the most general form?
Coefficient for the variable.
Yeah, so we could look more generally, and I'll put 2 subscripts here, A and B. So I'll call this now f sub 3. So I'll say FAB of x will be AX plus B mod 26. And the reason I want to go in this order is I want you to see that these are natural choices. You know, where did this come from? Why did we make the choice to look at this? Well, we had the Caesar cipher. It was a linear method. What's the next simplest linear function we could look at? Well, this is a linear function where the coefficient of x is 1. Let's look at a more general coefficient. Do you think if every choice of A and B were possible, how many choices would we have? I'm sorry?
I'm just repeating, every choice of A and B.
Yeah, if every choice of A and B worked, how many choices would we have? 26 squared. So we would have 26 squared choices. That's better than 26, or better than 25. So if you want, you know, we can keep going back and forth as, do we want this to be 26 or 25? Do you think every...
Like an identity element.
I'm sorry?
Like an identity element, right?
Well, so there's always an identity element. It would be just, you know, 1, 0. So there is the shift that will, there is the transformation that will do nothing. Do you think every choice of A and B will work? Okay, which do you think is going to be more likely to have failures, A or B?
A is 0.
Yeah, if A is 0, then basically you're sending everything to the same letter. And it would be just like a string of Q's. It's encrypted. It also can't be decrypted. Okay, so we know A equals 0 is bad.
26 squared minus 1.
So we're making some progress. But the real question is there anything else that's bad? We need to be able to invert. Is the B difficult to invert, yes or no? No, we can always get rid of the B by just subtracting off B. Right? So can subtract B. Okay, so if I want to, it's enough to study for now just the simpler case of f a of, and this is where the, I'll call it, well, let's do it this way. fa0 is just ax mod 26. Because I can handle the shift of b. I can remove that by subtracting b, and now I just have to fix this. So the question is every choice of a going to work here? Okay, which a won't work? Okay, good. Multiplicative inverses in what sense? Mod 26. So for instance, if I look at 2x, I need to multiply this by something so that this is the same as x mod 26. So let's do a simpler one. If I have, right, if I have 3x, what could I multiply 3 by so that this, the coefficient here would be 1 plus a multiple of 26? 9. So if I multiplied by 9, this would be 27x, which is 26x plus x, and that's the same as x mod 26. So if I have 3x, I can invert that by multiplying by 9. So what we can say is 3 inverse is 9 mod 26. So 3 is an invertible element. What this means is there's at least now 2 choices of A. What's the other choice of A we know works? 1. So we know 1 works. There's another choice of A we know works. 9. So what would 9 inverse be? So what's the inverse of 9? 3. So we know at least 3 choices of A, 1, 3, and 9, and we know 1 choice of A that doesn't work, 0. So the question is, what about other numbers like 2? Is there anything we could multiply 2 by? So we have 2x, and we want to multiply by A so that this would be the same as x, not A, let's call it w. So that this would be the same as x mod 26. Well, I really don't need the x. This has to be true for all x. So I really want to just solve this equation. I can just take x to be 1. I want to find a number. Well, what would this mean? This would mean 2w is 1 plus a multiple of 26. All right, multiples of 26 are even. This is even. So even, odd. There are no odd numbers that are the difference of 2 even numbers. So we can't find an inverse for 2. And in fact, if I take any number that shares a multiple with 26, it won't work. So what's another good multiple of 26? 13. So if I tried 13 over here, I would then get 13w is equal to 1 plus a multiple of 26. Well, 13 goes into the far left. 13 goes into multiples of 26. It doesn't go into 1. So 2 fails and 13 fails. So we can start listing all the numbers and see which ones work. So I will shift to the Darth Maul pen. So we've got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Henry wonders how I can fill up a whole class. 19, 20, 21, 22, 23, 24, 25. So which numbers do we lose? We lose 0. What else? We lose 2. All the evens, right? Because as long as it shares the factor with 26, so any evens is gone. We lose 4, 6, 8, 10, 12. If we had said that, we wouldn't have had to write all these even numbers. But it's good to just see everything. All right, we lose 13. And we lose all the multiples of 13. Okay, it's too bad. So we're left with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 choices. So we have 12 that work. So we call this the Affine Cipher, or the Affine code. So we have 12 choices for A, and we have how many choices for B? Yes? We are including 0. So it's easier to do this. Now, of these, one of these codes will be A equals 1 and B equals 0. So really, there's 25 here, and there's 12 times 26 minus 1 here. It's just easier to say there's essentially 12 times as many affine codes as Caesar codes. And it really comes down to how many numbers are relatively prime to 26. It turns out counting numbers that are relatively prime is one of the big ingredients in a lot of the encryption that we'll see. If you've heard of RSA, this is one of the key steps. And you want to be able to find very quickly, are two numbers relatively prime, or what common factors do they share? So if you are rich, you can basically indulge your interests. And there was a donor at Brown who was a huge Henry David Thoreau fan. And he got a lot of Thoreau stuff and donated it, including Thoreau's college algebra book from his Harvard days. And so the library at Brown reached out to me because I was a math professor, and I happened to be the one to get the call, and they asked me to take a look at it. And so you actually see Thoreau's writing in the margins of his math book. And one of the things I saw was his writing of the Euclidean algorithm to find greatest common divisors. As an aside, I hold Henry David Thoreau up as the patron saint of mathematics for his great advice. Simplify, simplify. Before you spend hours doing long calculations, spend a few moments and see, is this the best way to do it? A lot of times if you're teaching calculus, if you have a product, it's sometimes better expand the product before you take the derivative rather than using the product rule. So spend a little bit of time looking at the algebra. So later today, we will talk a little bit about finding when numbers are relatively prime and finding them quickly. Yes? I mean, the name affine is basically coming from lines. And so there is, I think, some connection in terms of just the objects that you're studying. We're basically studying linear objects. So you could ask, well, what if we had a more complicated thing? What if we tried to put in a parabola here? The problem is we need something that's going to be invertible. And so the next possibility is we could try to put it a quadratic. And I don't really care what's best. What I care about is the thought process. So if you're teaching something like this, you can ask your students, what should we try next? And trying a quadratic would be the next logical thing. Will you always be able to invert a quadratic? Will you always have a unique solution? Well, one of the things from the quadratic formula is there can often be two solutions to things. And it would be very bad if you had encryption like that. There are some codes where there's one code that uses a 5 by 5 square. What's the problem with the 5 by 5 square? Yeah, you're missing a letter. So with the 5 by 5 square, you have to have two letters go to the same. And the hope is that from context, you can understand which letter was meant. I'm sorry?
It's like old telephones.
Yeah.
So old Vietnam era POWs
Right.
would use a knocking code.
Yeah.
And they just they did a 5 by 5 square and they used K and C interchangeably.
Okay, it was
They
KC.
eliminated K. I forget which one they eliminated. But
Right.
they essentially eliminated
Yeah,
one of the two.
exactly.
And used those two
Right,
interchangeably.
right. And if you think about the sounds that they make, having the K and C go into the same thing is perfectly fine.
You can figure it out.
You can figure it out without much trouble. Yeah. I know they also did
So they're
blinking.
indicating which row and which column.
Right.
Exactly.
So you like
Yep.
once, so like once, and then twice would be, first row. So there's an easy way of doing it.
Yeah.
Easy way of understanding it.
Are the letters arranged alphabetically or just
I believe they were arranged alphabetically. Wasn't there?
the only thing is you sometimes have to be careful in terms of what you talk about because things could still be in use. The second worst question I ever heard a journalist ask was after 9/11, where they were talking to a pilot from an airline, and they said, "Do you have any secret ways of informing people on the ground that something is going wrong, that people are trying to take over the plane?" And the pilot was brilliant. He said, "No, there are technical reasons why we can't do that. What's your next question?" You're just, but yeah, second worst question I ever heard in my life. I'm sorry? The first was during the first Gulf War. There was like a 10-year-old girl whose mother was serving, and the reporter said to her, "If you could have just one wish, what would you wish for?" "My one is for my mommy to come back home." And then was the worst question I've ever heard. "Alive?" I mean, this was just milking the... I really hope the husband beat the reporter up. I can't say that, of course. I don't condone violence in any way, shape, or form. Except that. But it's interesting when you read, say, Winston Churchill's write-ups of World War II, because it was written not that long after the war, and it was kept secret. At this point that the German code had been cracked. And later we'll talk about the Battle of Midway and how the US had cracked enough of the Japanese codes to know what was going on. So we've done the Caesar Cipher, we've done the Affine Cipher. So the more general thing is, just going forward a little bit, is the alphabet code. So basically, each letter goes to a unique letter. Each letter goes to a unique letter. So how many choices do we have for where A goes? 26. How many choices do we now have for where B goes? 25. Because whatever letter we send A to, B can't go to that. Now how many choices do we have for C? 24. And so on and so on and so on, all the way down to 3 times 2 times 1. So we write this as n factorial. So has everybody seen the factorial notation? So this grows extremely rapidly. And so it is amazing how fast something like this will grow. So I'm not sure why it's shifting location to over there, but no, it's coming back now. So anybody want to guess roughly how big 26 factorial is? Big. My computer's just getting out of standby. How big? Ballpark estimate. Well, from 26 down to 10, each of these are 2-digit numbers. So if I wanted to quickly estimate this, this is going to be at least 10 to the 16.
Right.
A lot of them, the 20s and whatnot. And I can give you the first few, like 6 factorial is 720. So from 6 down, it's going to give me another 2 digits. So with a little bit of work, we're already at 10 to the 18, maybe around 10 to the 26 when you put in everything. You want to be able to get a quick estimate. And with doing a little bit more care, thinking about how big all those numbers are here, it's not going to be that bad to do. So I will get the exact answer. All right. The exact answer is 4032914611266056358. I'm sorry, 584000000. Also known as about 4 times 10 to the 26. So it's about 4 times 10 to the 26. And you want to get a sense of, is this secure? So there would be 4 times 10 to the 26 codes to check. Without a computer? That's pretty good. So it seems like you have a tremendous gain.
Hard to decrypt?
It's hard to decrypt. Well, what you would need to do is, if you know the encryption and the decryption, you would have a lookup key. And so you have maybe A goes to Q, B goes to C, C goes to L, Z goes to Z. Maybe something actually goes to itself.
And you get into relative frequencies.
I was just gonna
So,
say, yeah.
so now that's the question of, can you attack it? So just because you try to do a problem one way doesn't mean that somebody who's trying to break the code has to go the same way. Maybe they can find a better way to attack than going through all possibilities. So if you want to go through all possibilities, you can do some estimates. Even with today's computers, 10 to the 26 is going to be pretty safe. What you want to do is you want to get an estimate of how many codes do you think a computer could check in a second? Let's say you could check 10 to the 12 codes in a second. That's pretty good. If you're a little bit worried, let's bump it up to 10 to the 15. I am not worried with 10 to the 15. I don't think our computers can do 10 to the 15 in a second. How many seconds are there in an hour? Well, let's do how many seconds in a minute. Try again. Approximately how many seconds in a minute? I don't want to have to be multiplying by 60. 100. So there's about 100 seconds in a minute.
10 squared, I mean.
Right. So there's about 100 seconds in a minute. How many minutes in an hour? 100, right? So we're at 10 to the 4th seconds in an hour. How many hours in a day? 100. 10 to the 6th. Okay.
Don't we wish?
So we're just rounding it up a bit.
How much can we get done?
And then, so we're at 10 to the 6th. And then how many days are there in a year? I'm sorry? 1,000. So 10 to the 9. So overestimate at 10 to the 9 seconds per year. So if you had your computer doing 10 to the 15, checking 10 to the 9 things, if you multiply that, you'll get 10 to the 24. We got to get to 4 times 10 to the 26. So even with all this terrible estimation, we would have to be running for 100 years. Now, that actually helps us. Because over 100 years, the computers will actually start to get better. So you can actually take that in. No, okay. This tells you that if you just do a brute force analysis, it's going to be secure. So the only way you're going to fail is if there's a backdoor. So a lot of these codes are designed so that if you know extra information, you can find a way to bypass the long brute force search. Theoretically, these codes are trivial to break. Enumerate all possibilities and see which one works. But from a practical perspective, the number of possibilities is so large. And what you want to do is you want to try to give people a sense of just how big is a number like 10 to the 26. A lot of times when you have numbers like this, it's hard to put them in perspective. Probably the best example I ever heard was there was some very energetic radiation going through the solar system. How energetic? If you had a lead shield from the sun to Pluto, it would pass through that. It's like, okay, this is strong radiation. So as was remarked, these codes are actually trivial to break. And the way you break them is with a frequency attack. I'm sorry?
You're assuming they're in English then.
You're assuming they're in English, but hopefully you have some idea of what language is being used. Deliberately misspelling things could be helpful. If you have spaces, that's a tremendous help. So if you've seen the daily cryptogram or whatnot, these are usually not that hard to break because they have spaces. And if you see anything that's just a one letter, okay, that's either A or I. If you see 3 letters, the or and are very likely. And the more letters you get, the more likely it is for you to get another letter quickly. So these are not that hard to break. And so you can do a frequency analysis. And as was remarked, different languages will have different winners for different frequencies. So in English, what do you think the winner is? E. So your best guess is if you have a long message. Now there is the English novel that was written without the letter E.
How was that?
I don't know.
Yeah?
You can Google it.
Research it?
Yeah, it's a novel thing.
I wish that they, in the original version, that they was very thrilled about the end, all excited and then up. But so you could do that. And you can use strange phrases and whatnot to make it a little bit harder, but the frequency analysis is going to work. So there was a modification to the alphabet code to make it a little bit harder. And so what I want to do is I want to just give you a little bit of a sense of what's out there and not go into all the details. So let's do, break soon for 5 minutes. All right, so let's say I want to secretly send this message to Kent. All right, writing it on the board is probably not the best way to secretly send this to Kent. So the idea was to take a code phrase and write it below. So I'm going to take my code phrase as Red Sox. This is where it would have been nice to have a red marker. Or else I will do, and you just keep repeating it as needed. And so what I would do is I would shift L by whatever number corresponds to R. I would shift E by whatever corresponds to E. D I know is 4, so T goes to U, V, W, X. So T would go to X. I think we have a green.
You would go to X
Because D is 4. Right. E is 5.
Okay.
So E would go to F, G, H, I, J.
Okay. Wow.
And so I could just shift like that. What's nice is here the E is encrypted to J, but here the E is going to be encrypted to something else.
Oh.
So this is, E is, I will just write not J. I don't care what it is.
Right.
Okay?
So you need to know the special code.
You would need to know the special code. And the advantage is not only is the special code hopefully secret, but the length of the special code is hopefully secret as well.
And it could change often.
And it could change often. But one of the biggest troubles in cryptography is how do you have people agree upon what the codes are? Well, if they can meet and they can have code books, that's great, but the danger is always, well, what if the code book is captured?
Right.
And in World War II, there was a huge effort to capture a German sub, because if they could capture that sub and get into the safe, they could use that as a tool to get into the naval enigma.
Both ways.
Both ways.
Yeah, the Germans were trying to do that too.
Yes. So over here, if I don't know the code phrase, it's much harder to do the frequency analysis, because now the letter E is not always encoded the same way. So you could start to put in different code phrases, but you now have a lot more choices. It turns out that there's some advanced mathematics you can do to try to guess the length of the code phrase.
Really?
And so this is one of the dangers, that things that might seem secure,
Somebody can come up with a
somebody can often come up with a backdoor approach to it. I will end this unit with a story that happened a couple of years ago. They found outside of Vicksburg in like a river a message from the Civil War. It was a Confederate message, and it was encrypted. And it was encrypted using something like this. This is called a Vigneri cipher.
What kind?
Vigneri, my spelling is atrocious, so I will just look at how to spell it. All right, so V-I-G-E-N-E-R-E, I think. And there's either an accent mark or a derivative on the, I think, E or no? Oh, it's this one, sorry. Okay. So there was this encrypted message found in the river. Now, with late 20th century computers, it's not hard to crack this. But some people decided to just, for fun, let's imagine we don't have the computers. Can we crack this knowing what we know?
Like they would have done.
So in World War II, one of the mistakes the Germans did is there was a facility that always broadcasted the weather report at the start of the day. And if you know what the weather is in that area, you now have a little bit of a hook into what was going on. And it turns out we had actually, in the archives, found what a lot of the Confederate code phrases were. And if you just try one of them, it worked. It was using one of the standard ones. The message was being transmitted or sent on early July 1863. And I think anybody know what date? The courier arrived on July 4th, saw the Union flag flying over Vicksburg because Grant had just taken it, and threw the message in the river. And the message basically said, Chief General commanding Confederate forces, greetings. We unfortunately have no reinforcements to send you. You're on your own. So the message content wasn't that surprising. But it's very easy to be misled into how secure something is. The alphabet cipher. We just did a quick calculation with modern computers, and we're getting something on the order of 100 years. Well, one way to do this is to slave more computers into it. A lot of times you hear about distributed computing. People did this for the search for extraterrestrial intelligence. You could have an app running on your computer to analyze signals, or for the Human Genome Project, or for stuff that I care about, zeros of the Riemann zeta function. And for a while, when I was in grad school, I had a bunch of computers slaved together, and we were one of the top 10 contributors to finding zeros of the Riemann zeta function. Zeros of the Riemann zeta function. It's something that's very important to number theorists. It caused too many computer crashes, so eventually we stopped doing it, but you can get a lot of people around the world. So the fact that it took 100 years, well, if those numbers were really fine, if we got 1,000 people, now all of a sudden that's only a tenth of a year. If you get 10,000 years, so for problems like this, they might not be so bad if you have distributed computing capabilities. You could make the ciphers even more complicated. You could start having pairs of letters go to pairs of letters. You can also look at frequency analysis of pairs of letters when you're trying to figure things out. Which letter pairs are most likely? So what do you think is one of the most likely letter pairs in English? The TH. And there's a great comedy routine by Bob Newhart about stuff like this, where you might have heard of if you have an infinite number of monkeys and an infinite number of typewriters, eventually one of them will give you the complete works of William Shakespeare. Which means that Shakespeare is in some sense equivalent to a very lucky monkey. But of course the question is, how long will it take? It will take a long time. What you can do is you can help the monkeys. So the zeroth order monkey is just typing randomly on the keyboard. The first order monkey, let's say they hit a T. Then you give the monkey the special keyboard that follows the T, and the letter frequencies are adjusted to be more accurate to what would follow a T. The second order monkey, if they type the TH, you give them the keyboard that has the frequencies corresponding to TH. And by the time you get to a third or fourth order monkey, it's phenomenal how well they're doing. By fifth order monkey, it's terrific. And what you can do is you can train the monkeys differently. You can have the Edgar Allan Poe monkey, who has the letter frequencies following Edgar Allan Poe. You can have the William Shakespeare monkey. And you can see the different writing styles. So the real lesson about all this is things that seem secure might not be. And then before we do the break, I will end with just one plug as to why we care so much about mathematics. I'm going to quickly explain two different crypto schemes. I'm going to ask you which one is more secure. How many of you have seen Monty Python and the Holy Grail? Okay, so I'm thinking of the scene when they're trying to get over the bridge, and you have the guardian. Okay, so here's method one. I let n be the product of two primes. So this is known, and this is secret. And the password is P or Q, and say each is around 10 to the 200. So I'm choosing a 200-digit prime number. It turns out it's actually not that hard to find a 200-digit prime number.
200-digit prime.
200-digit prime number. It turns out it's not that bad.
Never tries.
The alphabet code looked really bad, but it turned out there was an easy way to do it. So it's not that bad to find. We can do this very fast, unconditionally. We know how to do this. That's method one. Method two is x is a 5,000 digit random number, and that's secret. And the password is X. So you have two passwords here. Either P or Q work. You only have one password here. I tell you the product of P and Q, so you know it's going to be one of the divisors of N. If you could factor in, that's fine. But if not, you could still just do a brute force analysis. How many 5,000 digit numbers are there? 10 to the 5,000. 10 to the 5,000 choices. The number of choices here, we have roughly 10 to the 200 choices, like a 200 digit number. Which do you think is harder to get? 5,000 digits correctly or 200 digits correctly? The 5,000 seems much more secure.
Right.
I'm sorry?
But not all of the numbers are.
I'm sorry, not all the numbers are prime?
Yeah.
Right, so if you try to use the fact that not every number is prime, that could cut down on your searching, but it might be such that it's harder to figure out which numbers are prime and which numbers are not. So I'll give an example. A couple of years ago, I was a postdoc at the American Institute of Mathematics, and somebody presented a really interesting riddle. If you take the digits 1 through 9, you can form three fractions, A over BC plus D over EF plus G over HI, and it will sum to 1. So maybe it's 1/23 plus 9, 87, I forget what it is. So there's a way to put in the digits 1 through 9 into these 9 slots. And so I'm there, and I'm surrounded by some of the top mathematicians in the world, and they start proving theorems about where the 5 can't be and stuff like that. I write an extremely inefficient mathematical program. I don't bother to make it efficient. How many times do I have to run my code? I'm trying to find how many times do I have to run my code? No. There's 9 factorial arrangements of the numbers. How many times do I have to run my program? How many times am I running my program?
You really only 6, because you're going to have to 0 on one of the.
Well, no, 0 is not one of the numbers. It's 1 through 9. How many times am I running my program to find the locations of the numbers 1 through 9?
3.
Not 3.
Just guessing.
How many times do I have to run the program? Once.
Yeah.
Once. I run the program once. Right? Now, the program is going to have 9 factorial things to check. You could do things by symmetry. You could say, well, look, without loss of generality, 9 has to be in one of the fractions. Let's put 9 in the first. So now there's 3 spots for you. You could do stuff like that. Because I'm only running the program once, it would take me more time to code something like that than to just have it naively go through all 9 factorial possibilities. It would take me more time to write it efficiently than to just write it inefficiently and run. So as they're proving all these things, okay, here's the answer, guys. Now, if they change the problem, then the theorems they're proving would be useful. But for the problem at hand, I could just do this once and I'm done.
But it only works for that problem.
It works for that problem. But for something like this, while I only have to check prime numbers, it might be harder to determine if a number is prime than to just see it as a divide n. So even though you don't have to check the composite, okay, so I'm not going to check the even numbers, that's clear. A number is divisible by 3 if the sum of the digits is, so there are some things I can do to make it a little bit faster. But it might take more time to exclude composites than to just do the division check. But do people agree that this seems more secure? Because you've got to get 5,000 digits correct. Here you only have to get approximately 200 digits. Now, we did a calculation about how long it would take to crack the alphabet cipher. If you did a similar calculation here, if you looked at the entire life of the universe, to give you some sense of how bad this problem would be to try all 200-digit numbers, if every subatomic particle in the universe was a universe, where every subatomic particle in that universe was a supercomputer devoted exclusively to your use, running since the dawn of creation, and we'll use as a time, on the order of billions of years, you wouldn't be close. It's a nice exercise to do to just give you a sense of just how hard it is to try all 10 to the 200. That said, this method is far more secure than this method. This is a terrible method. Anybody have any idea as to why this is so bad? It has to be written down. So imagine you have the 5,000 digit password and you're the computer. I have the ability to torture you. I think Henry said I'm not allowed to do that after what happened last time I taught.
But you can still shape code into my.
I can shape code at you. But if the computer is captured, it has to have the password written somewhere on it so it can check what you input with what it has stored. So the problem is, in this situation, you need to know the password. So you would need a smart gatekeeper. And this is knows when hears. Almost surely this will not be visible, however, but this is, I'll know it when I hear it. The computer doesn't need to know the password. You can torture the computer to your heart's content, and it's not going to make any difference. All the computer needs to know how to do is divide. And then if it divides correctly, then I let you in. If it doesn't divide correctly, well, it's not the password. So this is why, even though this is far fewer things to try, it's far more secure. Now, the interesting question is, what level of security do you need? And sometimes people have not been so good at estimating the rate of technological progress. And you might be using something that you thought would have been secure for 20 years, maybe it only lasts about 5. So they have different levels of primes, different sizes to give you different levels of security. All right, so before we take a break, any questions on the stuff up till now? I'm hoping you can find some stuff from this that's either personally interesting or that you can bring back to some of the classes that you're teaching in terms of the amount of mathematics we need. And here's some ways to motivate some of the functions you might see. If you've seen linear functions, here's ways to do things with linear functions. I will give you a generalization of this. I'll give you some homework for next time. Just some things to think about, some math rules that are related to stuff like this. All right, so this is a good place to stop for the first.